Good morning, everyone. Welcome to Brandforsk and our result webinar about functionalized, fire-retardant and bio-based composites. Now, my name is Mattias Delin. I'm the research director here at Brandforsk, and with me today I have Oisik Das and Rhoda Afriye-Mensah from Luleå University of Technology. Good morning, Oisik and Rhoda.
Morning.
Morning.
So, please tell me, who are you? Rhoda.
I am Rhoda Afriye-Mensah. I'm a postdoc researcher at the Division of Structural and Fire Engineering in Luleå University of Technology. I'm currently working with Oisik Das.
Okay, welcome.
Thank you.
And Oisik, who are you?
Hello. I am a senior lecturer at Luleå Tekniska Universitet at the Structural and Fire Engineering Division. We do a lot of fire research, structural engineering research, and education on fire. Rhoda is working with me as a postdoc, and we have now quite a nice group of fire researchers in LTU.
Yeah, you have a lot of things going on.
Yes.
Nice to see.
Yeah.
So welcome here today, and
Thank you
we
very
will
much.
see more of you in a
Yeah.
while. You have a presentation about your project, and we will also have some questions and discussions after that. But before that, I will give the audience just a short information about this webinar. So thank you for now, and see you later.
Thank you.
Thank you.
Some of you probably, hopefully, were already familiar with us at Brandforsk, but this is a short introduction. We have a vision, a fire-safe and sustainable society built on knowledge. We develop and communicate knowledge, mostly research, to limit the negative consequences of fire in the society. We started in 1979, and we are a foundation since 2019. We have supporting organizations that fund everything that we do. This makes us a collaboration between many parts of the society, and the funding so far this year is about 650,000 euro, but the fundraising is still going on, so please chip in if you like to. We use the money for research, of course, and also for result communication like this webinar. And we have a research school for practicing fire safety engineers in fire services, and they are part-time PhD students beside their work in the fire service. And we also have scholarships for students. Now, these are the organizations that have supported us so far this year. Thank you so much. And the fundraising is still open, so I hope that more are interested to supporting us. And the program for today, after this short introduction, we will have a presentation of the project, about half an hour, and then we will have time for questions. And as I said, please ask your questions in the Q&A, and we will answer them. And now let's see the presentation of the project.
Welcome, everyone. This is the final report presentation for the Brandforsk project entitled Functionalized Biochar for Fire-Retardant and Bio-Based Composites. I'm the project leader with my postdoc Rhoda Mensah, and today I will talk about what we found in the project, which was generously funded by Brandforsk, and we are eternally thankful for this. So let's begin. Let's look at the problem first. Today, plastics are everywhere. Like the cables are made of plastic, phone covers are made of plastics, and everywhere we see plastics. But the problem with plastics are most of these products are made from non-renewable sources. The other problem is these synthetic-based plastics. When they are dumped in landfills, they can produce microplastics, which are damaging for both the flora and fauna. So the solution for fossil-based plastics is to make bioplastics. These are renewable, they are environmentally safe, and they are biodegradable, which means they are not causing the harmful microplastics. However, we also have problem with these bioplastics that they burn. Also, normal plastics burn. So most plastics, because of this hydrocarbon chain or hydrocarbon backbone, they are prone to burning. So the solution is to use fire-retardant treatments. Now, fire-retardant are very effective. They can either stop the three things needed for fire, that is the heat, oxygen, and fuel, and they do it by many different mechanisms. They either quench the flame, or they can create an intumescent layer that cuts off the heat and the fuel supply, mass and heat transfer. They can also be mineral based, phosphorus based, and there are many different types of fire retardant already being used, and many of them are very sustainable, does not cause any environmental problems. But although on one hand, fire retardants are very effective in reducing or in imparting fire safety in plastics, there is a problem with this fire retardant. So if you look at the photo right now, it's a microscopic image of a plastic with a fire retardant particle, and I have indicated the fire retardant particle as FR. And the polymer matrix, what do you see? We see that cracks are forming from that fire retardant particle. So although fire retardants are very effective in imparting fire safety in plastics, they lower the mechanical properties by acting as stress concentration points, which is not good, because we want to have a holistic improvement of polymer or composite properties. Not just fire properties are improved, but mechanical properties are down. So we are not really winning. We have to win. We have to win by improving all the properties, all the performance properties. And this is where our project is aimed at, or was aimed at, to create a balance between the mechanical and fire properties in plastic. So how we will do that? We will do that by a material called biochar, eller biokol på svenska. So how do we make biochar? We take any kind of waste biomass. It can be waste wood, it can be branches, leaves, any kind of waste biomass. And we heat that biomass at high temperatures, over 500 degrees centigrade, below 1000. It can be lower than 500, more than 1000, but usually the range is from 500 to 1000 degrees centigrade in absence of oxygen or with low amount of oxygen. And then we get a black solid material, which looks like charcoal, but technically that is, our reaction is more controlled. And we get a solid particle, not a particle, like solid powder, which looks like the photo you see, a macroscopic photo with a lot of pores, and it has a carbon skeleton. So the idea for the project is that we will use this biochar as a beneficial Trojan horse. So the main point is, if we can dope the fire retardant particles in the numerous pores of biochar. So what will happen? These fire retardant particles will not be in the matrix, and they will not act as stress concentration points. In fact, they will be housed inside the biochar pores. And this was the main idea for the project. So with the doping of the fire retardant into the biochar were done in 3 different ways. And the whole project was divided into 2 phases. In the phase 1, we have used Lanosol, which is an algae-based fire retardant. Algae we can derive from oceans. And the plastic used was wheat gluten, which is a bioplastic, extremely sustainable and biodegradable. And we have tried to dope this Lanosol fire retardant in wheat gluten bioplastic in 3 different ways. The first was dry mix. So basically we mix the biochar and the fire retardant particle together. And the second was chemical doping, where we dissolved the fire retardant in acetone, and then we added the biochar to that solution and then let the acetone evaporate. And the third method was to melt the fire retardant at 135 degrees centigrade over the biochar for 1 hour and also for 3 hours. Moving forward, after the doping were doping methods were done. We have done a microscopy to see how the doping has happened. And on the number A figure, we see that quite a lot of fire-retardant particles are on the surface. They didn't really go inside the pores of the biochar. With number B, we see that with the chemical doping, we see that that although they're not on the surface, they have kind of coated the surface of the biochar. But if we look at number D, we can clearly see that the fire-retardant particles are inside the pores of biochar. So from this analysis, we realize that the thermal doping method, where we heat the fire retardant for 3 hours, is the most effective one. Then we made the composite, and this is the different levels of the different composites that we have made using the doped biochar, as well as the neat polymer, which is just with gluten, as well as we have made gluten with just biochar and just the fire retardant, which is lanosol in this case. So after we made the composite, we have tested the mechanical properties. What we have seen is that with the chemical doping method and thermal doping method, the tensile strength of those composites were the same as the control sample, which is neat bioplastic, and the tensile modulus were much higher than the control sample, which is a good news, because that is what we are trying to do. We are trying to conserve the mechanical strength and improve or improve the mechanical tensile modulus by adding fire retardant and biochar. Although we have seen that the ductility has reduced, but nevertheless, the tensile strength has been conserved. The ductility has reduced which is quite expected, because when we add any particles to any plastic, the molecular mobility of that polymer chain reduces, increasing the stiffness or the reducing the ductility. But the main takeaway from this is that after doping with chemical method and thermal method, we were able to conserve the tensile strength as the neat plastic or the control sample. We also did the electromicroscopy analysis of the composites to see how the doped biochar is manifested in the matrix of the composites. And we can see from here is that when the sample, which is number B, which was just the fire retardant, is kind of causing a lot of cracks. Like we have seen previously, that fire retardant particles were causing cracks, which is not good for the mechanical strength. Number B, where we have only biochar, no fire retardant, we see that a biochar particle has a mechanical interlock with the plastic, which is quite a known phenomenon, understood from my previous work in my PhD, that when we add biochar to any plastic, the pores of the biochar interlocks with the plastic, improving the mechanical properties. And with dry mix, which is number D, we see the particles are on the surface of the plastic. However, if we look at number F, we can see that the biochar is properly manifested with the fire retardant doped inside the pores. We have a magnified view. This is what we have tried to do in the project, that the fire retardant particles are doped inside the biochar and not present on the surface, so that they can still function as fire retardant without reducing the mechanical properties. Moving forward, this is where Rodha will take over. Rodha, can you please continue from here?
Okay, so we conducted experiments to determine the thermal and fire properties of the wheat gluten and its blends. And for the thermal properties, we used thermographic analysis, or TGA experiments. And TGA measures the mass loss of a sample as a function of temperature or time. So these are the results from our experiment. If we look at the graph, we see that at lower temperatures, that's between 40 degrees Celsius up to about 200 degrees Celsius, we see that the samples had similar mass loss trend. And even on the table at 140 degrees Celsius, we see that the samples, almost all the samples, lost about 5% mass. The main decomposition occurred between 250 degrees Celsius and 350 degrees Celsius. And at higher temperatures, at about 750 degrees Celsius from the table, we can see that the LBWG, which is the dry mix, and the CLBWG, which is the chemically doped sample, had the highest residue. And this is because these samples had Lanasol particles on the surfaces, and these particles acted as heat shield during the decomposition process. So it actually slowed down the decomposition rate. The next one. For fire properties, we conducted two different experiments. That's the microscale combustion calorimeter experiment, where milligram samples are required, and the cone calorimeter experiment, where we use gram-sized samples. For the microscale combustion calorimeter experiments, we conducted them at 1 Kelvin per second, and the results are plotted as heat release rate versus temperature curve for the undoped samples on the left and the doped samples on the right. So if we look at the undoped samples, we see that the peak heat release rate, which is the maximum heat release rate that is recorded for the neat wheat gluten and the biochar wheat gluten, are very similar. However, the addition of Lanasol to the wheat gluten improved the fire performance of the wheat gluten. And this is because biochar is a reinforcement and Lanasol is a fire retardant. So Lanasol protects the materials from the heat. If we consider the doped samples on the right, we see that the peak heat release rate recorded is actually, it falls between that of the LWG and the WG, neat wheat gluten sample. And if we take a critical look, we see that the green line, which is for the dry mix, LBWG, had the best fire performance. That means it had the lowest peak heat release rate. Yeah, so we use the results from the microscale combustion calorimeter to calculate the activation energy of the samples. What do I mean by activation energy? It is the minimum amount of energy that is required to initiate decomposition reactions in the samples. And in this case, we adopted the Kaisinger method from literature. So the calculation process is shown on the figure and on the left. And the results are the bar plots that are shown on the right. So if we look at the bar plots, we see that the activation energy of wheat gluten and the WG and LWG samples are very similar, but the BWG samples had an increment of 13%. And if we look at the doped samples, the LBWG, CLBWG, and TLBWG, it is actually very clear that the activation energy increases with an increase in the doping efficiency. So if we look at the TLBWG sample, which is the thermally doped sample, all the Lanasol particles were doped inside the pores of the biochar. And in this case, it has the highest activation energy. So we can conclude from these results that the initiation of decomposition reactions is slower with higher doping efficiency. The next one. Cone calorimeter experiments were conducted at 50 kilowatts per meter squared to observe the material's reaction to fire properties. And the results are plotted as heat release rate versus time curves shown on the slide. If we look at the undoped samples, that's LWG, WG, and BWG, we see that there are no significant differences between the heat release curves, and the WG samples has the highest peak heat release rate. But if we look at the doped samples, we see that the TLBWG, that's a thermally doped sample, had the lowest peak heat release rate. That means it has the highest fire performance. The next one. We observed the char residue from the cone calorimeter of the chemically doped and the thermally doped samples in the scanning electron microscope. And the micrographs shown as A and B, from these images, we see that the CLBWG sample has a less dense char with big holes in them. And then the TLBWG, that's a thermally doped sample, has a very compact and dense char with small holes in them. So from here, we can say that the structural integrity of the thermally doped sample was preserved during the burning process.
Thank you very much, Rhoda. So for the phase 1 part of the project, the conclusions are we have identified an efficient method of doping, which was thermal doping, because we have seen that it preserves mechanical strength, it increases activation energy, it has a char structures which is more compact and rigid, and it has a peak heat release rate, which is the lowest amongst the tested sample. And we can thus conclude that the biochar was successfully functionalized with the fire retardant, and we have been able to create a balance between the fire and mechanical properties in gluten plastic. So we have to do in the next phase is to identify if this doping is also possible with other fire retardant and in other type of bioplastic, and investigate the effect of plastic processing. So in the phase 2, we have used ammonium polyphosphate as well as lanosol. And based on the experiments, we have identified whether lanosol or ammonium polyphosphate is better. Depending on that, we have used polyamide 11. Initially, we planned to use polylactic acid, but it was not available. But polyamide 11 was used, which is also a bioplastic made from castor oil. And then finally, we have tried to understand, once we have identified the better fire retardant and the better bioplastic, which processing method is more optimal, either is it compression molding or injection molding. And finally, to identify the most suitable fire retardant, most suitable bioplastic, and the most suitable processing technique. So different processing conditions for this, where for the compression molding, we have 140 degree. Pressing time was for 20 minutes, and the pressure was, well, actually its force was 250 kilonewton. For polyamide 11, we have used 250 degrees centigrade. This depends on the melting point of the plastic. We have to choose a processing temperature which is equal to or higher than the melting point of the plastic we are processing. So for polyamide 11 or nylon 11, we chose 250 degrees centigrade. The pressing time was the same, and the pressure was also the same. And for injection molding, we use the temperature same as compression molding, 140. Injection times were 3, 5, 15, and 20 seconds, and the injection pressure was 600 psi. And these conditions were chosen after trial and error method to find out a sample that comes out which is cohesive and which is formable. And this is me holding one of the sample, and this is on the right hand side is the injection molding machine that we used. So I will talk about two issues that we had. I wouldn't call them issues, but two results, in fact. So when we tried to compression mold the APP doped biochar in polyamide, it was the samples all the time shattered, as we can see, shattered like glass. And the reason we speculate is that because of the heat shielding biochar, the molten polymer was not able to form in a lateral direction, although it was able to form in the vertical direction, but in the lateral direction, it had a lot of biochar, so it was not able to flow throughout the length and breadth of the sample to form. And that's why it, after processing, it shattered. And then when we have the gluten with the APP doped biochar, similar thing happened. So as we can see, for all the processing times, injection times, the samples did not form. And this is because of the higher amount of biochar in the sample. So what we have realized is from these two that polyamide 11 is not a suitable bioplastic. Gluten is better. And from this, we have also identified that compression molding is a better technique than injection molding. However, to understand better why the compression molding of polyamide 11 and the injection molding of gluten were causing problems to form the samples, we have done further analysis. So first, we have done differential scanning calorimetry to understand the thermal properties of the composites. We can see that when we adding the APP doped biochar in neat polyamide 11, the melting point have reduced a little bit, but we can clearly see it has increased the crystallization temperature. And this is because this biochar particle acted as nucleation sites from where crystals were formed. And for the gluten, there was no change in the melting temperature, and because gluten acts as a thermoset plastic after 150 degrees centigrade, there was no crystallization peak. However, from the DSC analysis, we did not gain any insight regarding why the compression molding of polyamide 11 and the injection molding of gluten with APP doped biochar was not able to form the samples. And we also did scanning electromicroscopy to see the manifestation of the APP doped and biochar in the different samples. From the neat polyamide 11 microscopy, we see a clear ductile fracture. However, for the APP doped biochar in polyamide 11 made by compression molding, which is the second top figure, we see a lot of crystal-like structures are formed. And this was seen in the DSC analysis before that this biochar particle have formed crystal acting as nucleus sites. Now, the biochar with APP in gluten made by compression molding was quite good. We can see the APP doped inside the pores of the biochar as intended. But when the same sample was tried to be made by injection molding, we see large gaps and ridges, which means it did not fuse together. And that is the reason it was not able to be formed. So we also did an infrared spectroscopy analysis of the different samples. So for polyamide-based samples, we see that the peak characteristic in the region 739 to 1200 centimeter inverse web number, there has been a change in the peak, which can indicate that there's a ineffective cohesion between the polymer and the biochar doped with APP. And in the region from 745 to 1180 centimeter inverse, the intensity of the injection molded sample was little more compared to the compression molded sample where the plastic was with gluten. So we can conclude that the processing has an effect on the formation of the composite, and this has caused some samples, two samples, in fact, the compression molded polyamide 11 and injection molded gluten, which had APP doped biochar, to be not formed. And then we have also analyzed the mechanical properties, and we can see that the APP doped biochar in wheat gluten made by compression molding has similar tensile strength compared to the Lanosol doped biochar, and which is good because this is what we are trying to conserve the mechanical strength. Moving forward, we have also done the thermal analysis, in this case, thermographic analysis. Here we see that the polyamide 11 based materials had the highest onset temperature of decomposition. And however, the gluten based sample has the highest residue. So if you look at the graph on the right-hand side, see for the neat polyamide 11 has a much lower residue than the sample having APP doped biochar. The same trend has been found in the gluten-based samples, that the neat gluten has very low residue, and as we add biochar and the doped biochar, the amount of residue increases, which indicates that it is forming more char after the thermal cycle. We also did a cone calorimeter study, and we have a clear winner here that the APP doped biochar in wheat gluten made by compression molding has very low peak heat release rate. So we can clearly say that the APP doped biochar has been extremely effective in imparting fire performance or fire safety in gluten bioplastic, which were made by compression molding technique. So to end the project and the results we have been able to find an effective doping method, which was a thermal doping method, and which means that the biochar was successfully functionalized. And we have found that APP doping is a better fire retardant compared to Lanosol when it comes to fire performance. So if you are looking for having a composite that is extremely fire safe, then we choose an biochar doped with APP in wheat gluten made by compression molding. But if you're looking for overall acceptable properties, then we can go for Lanosol doped biochar in wheat gluten made by compression molding. So depending on the target application, we can choose either Lanosol for an overall mechanical and fire performance balance, or if you're choosing very good fire performance, then we can choose APP doped biochar in wheat gluten made by compression molding. So this was the end of the project, and this composite that we have made using functionalized biochar can be used, if you remember the first slides, with that we can make plastic household products, sheathing for wire, we can make phone covers and other electrical casings in buildings. So we have a different materials that can be used by the construction and building industry, which are both mechanically strong as well as they are fire safe. So with that, I would stop my presentation, and I thank Rhoda for wonderful help with this project, and LTU for providing the resources, and also Brandforce for providing the funding for this project. Thank you very much.
Thank you, Oisik and Rhoda. And we already have a few questions, and please ask your questions in the Q&A and we will answer them. So welcome, Oisik and Rhoda. We will start answering the questions. The first question I have here is how much biochar was used into the composite?
We used 4% for Lanosol, and we have correspondingly increased that to 15% when we used ammonium polyphosphate, APP. Because the amount of Lanosol we have to add was lower, so the amount of biochar was lower, but the amount of APP was like higher, so we had to increase the amount of biochar too.
Okay, yeah, right. And thank you. And what was the temperature during the compounding of the mixture?
Give me a moment. So for gluten, it was 140 degrees centigrade, and for polyamide 11, it was 250 degrees centigrade.
Right. And what was the reason for the difference?
Yes, we based this on, we did quite a lot of experiments to find out which are the best processing parameters. And usually when we process polymers, we take a temperature above the melting point of the plastic that we are processing. So gluten softens around 70 degrees centigrade and melts around 130, 40. So we use 140. And polyamide 11 vinyl melts at 185, but we have taken a higher temperature because biochar were there mixed. So it has already given it thermal stability. So we had to go a little higher than the melting temperature so that we make sure that everything is molten when we are processing. So based on the melting point and what is added in the mix.
Right. Yeah, thank you. And what heat fluxes did you use when you in the test in the cone?
It's 50
kilowatts.
50 kilowatts.
50 kilowatts per meter squared, yeah.
Okay. Thank you. And we also have a question here about what kind of biochar did you use? Was it something that you produced yourself, or was it a commercial product?
We got it from our collaborator in Germany. So it's they use it commercially, but we have a collaboration with them. So, and we can tell her what we want. I can tell. So he's my friend. He recently visited us in LTU, and I can tell him, okay, I want you make the biochar with this temperature, this amount of residence time. I want like this surface area. I can control the entire reaction conditions, and he just makes it for us. So it's very nice. But he also sells his biochar to other companies.
Right. And do you know what was this made from? From wood or?
Yeah, from wood. Yes, from a lot. I have to specify it's waste wood. It's not that we are cutting down trees to make biochar. It's from logging waste. So we are also quite sustainable when we are making the biochar. So, and the process of making biochar is also not adding to CO2 in the environment.
Yeah, and how's that?
Because the heat that is produced is recycled back in the reactor to give more heat for the reaction. So there's no smoke produced, so the heat is recycled back.
Okay, well, that's good. Have you looked at other applications of biochar with polypropylene or polyethylene?
My whole PhD was based on biochar application in polypropylene. So it works very good, and there's a lot of papers on that I have worked on it, published on it. So if you look into papers with my name and biochar, you will find all those papers. And we have found that the biochar in polypropylene improves mechanical properties, fire properties, reduces cost, improves sustainability. I have done like a nano indentation test on it, and like a variety of tests. So you can also read directly my thesis, so that all the papers are collected in that, so you don't have to search. Yeah. So if the person sends me an email, I can email the thesis back to him or her or they.
Yeah. Maybe we can link it to our webpage on this webinar page. Yeah. That's it, because your background is not really plastic, is it? It's more like biochar background, is it?
It's also plastics, yeah. Composites, plastic composites.
Oh, okay. Thank you. And what types of product can this treatment be used for? You mentioned some, but please elaborate that.
So basically, we wanted to use like bioplastics. Everything in our system is like bio-based, so that is a sustainability aspect. But one thing that we can use for is electronic, like household electronic, like casings and wire sheathings that can be used for what else? Non-load bearing structures for now. I mean, our target is to make it load bearing, but because we had to add plasticizer to the plastic, they're very flexible. So that's why it will be perfect as a wire or cable sheathing. So that and then the fire for cables are a big hazard. So I think that is where it is best suited as wire sheathing, cables sheathing, and electric switchboards and electrical appliances casing and covers.
Yeah. Is it a limitation, is it limited to hard plastics, or can you use it for more soft plastics as well?
Yeah, we can, for example, for wire, we can use soft plastic because, we had this glycerol for the gluten, but the Polymer 11, it's more, we didn't need to add any glycerol or plasticizer to it. So for that Polymer 11, we can use for electrical covers that is like hard plastic.
Yeah. Have you looked at insulation materials for buildings?
No, not particularly, but I think that is our next target, in fact, to work on insulation materials, and that would be our next research focus.
Yeah. Okay. Thank you. Now you call your project a functionalized biochar, and can you elaborate what do you mean by functionalized?
So when I was doing PhD, and I wondered, like, okay, like, can biochar act as a fire performance enhancer in plastic? And I added biochar to plastic, polypropylene, and I saw that it improves the fire performance in a more additive manner. So because biochar, high temperature biochar, when you make biochar at high temperatures, doesn't combust. So it's an additive way it is like improving the fire performance. But when I say functionalized, when we say functionalized, it's basically it has a better function. Not only it will improve the fire performance as an additive function, but also through the process of fire retardancy, whether it will reduce the occurrence of heat or transport of oxygen and fuel between the plastic and the incoming heat. So basically, it's like biochar doped that will act as a fire retardant itself, along with a fire non-combusting skeleton. So a biochar which has fire retarding properties. That's what we mean, like functionalized.
Okay, yeah, thank you. And about the environmental issue here, and I mean, what are is there any risk of calling things environmentally friendly because they origin from environmentally friendly products, but can it? I mean, like in the use and in the compounds that you make, can it turn from being environmentally friendly to be not very environmentally friendly? Is that such a risk, or is this a safe path for you?
It is a safe path. Like, now in today's world, it's extremely important that the products are innocuous to the environment and to the people using it. So we think it's quite safe to be used, and that is why in fact the problem with gluten is like it is too safe. So that is something that in my postdoc in KTH, I try to figure out how to make gluten less prone to degradation. So improve the shelf life or durability. But to answer the question, they're very sustainable. Like both polyamide 11 is made from castor oil, gluten is made from wheat. So and we have a lot of it. So and they're fully safe. Biochar, you can eat biochar. Like nowadays they're selling biochar or activated carbon. If you have some tummy problem, you can just. I have taken it myself. So yeah, it's like I'm eating my research.
Is that always wise?
Not always wise, but in this case, biochar has many other applications. Like, now we are also working with biochar in concrete. Yeah. Other people use biochar for contaminant remediation, for soil amendment, for improving the water retention capacity of soil. And there's a plethora of research going on. And it's extremely sustainable. It's fully safe.
Excellent. Well, that's very good. And your next project you mentioned here, concrete, and it's also a Brandfors project. And
exactly. And thank you very much.
Following up right now. That's very interesting.
We thank Brandfors very much for supporting us with that endeavor also, and we hope we get good results. And we hope to see or hear from some of you a year from now.
Yeah. So it's to be continued.
Yes.
That's very good. Yeah. And we have a question here about the differences between the first set of cone tests shown and the second test. Can you explain more about that?
Maybe Rodha, do you want to answer that?
Yeah. So the first test were for the wheat gluten blends, and then the second one was the polyamide 11 plus the compression molded wheat gluten blend. So there were two different materials for each set.
Well, thank you. And you were also talking about you have some it was cracking your samples and
yes, that is
and why was that, and what can be done to avoid that?
So we tried to do experiments to figure out why that happened. And we think what that happened was, I think the amount of biochar the fire retardant was a little more. So like I said in the recording, that when we add any hard particles to plastic, the plastic keeps on getting stiffer and stiffer. So we think the amount of biochar and the amount of fire retardant was little too high for polyamide 11. And that's why, and also when we add biochar and fire retardant, the thermal properties improve. So the processing becomes a little difficult. So the way we can improve this is to do studies to find out how much we can lower the amount of biochar and fire retardant while still having the same or similar fire performance and mechanical performance. So that is another research we can do to gradually reduce to a point where we can have the nice processing as well as have the similar fire performance and mechanical performance.
Yeah, so there's a room for more fine tuning in this.
Exactly. Yes.
Yeah. And another question is interesting. Do you see any future of use of biochar in paint?
Yes, we do, and we would like to explore that in the future, because we can make intumescent paints using biochar. Probably we can deliver the fire retardant in the paint using biochar, so it will be more effective, and biochar has very good UV shielding abilities. So the paint can be fire retardant, intumescent, as well as it can shield the structure from UV radiation. So that is something that we think is possible. And people are working on similar graphene for UV protection, but then biochar is easier to make than graphene. We can make in bigger quantities. Obviously, the properties are way inferior compared to graphene when it comes to performance. But making graphene is quite difficult. We in fact have a project where we're trying to make high amount of graphene. So it's quite difficult to do that. So yeah, but we definitely think that, and I think we will pursue this idea where we will dope biochar we'll use in intumescent paints.
Yeah, and will that paint always be black?
Yeah, and yes.
Yes, sorry.
Yeah. Yes. Yeah.
Well, that's a bit unfortunate, but okay, I guess we can live with that. Now we got a question here about the report from this project, and it is very soon to be published at our webpage. So just keep an eye out. And
can I add something to that?
Yes, please.
The first part of the report is already published in a polymer testing LCBA journal, so it is already available in the public domain. The second one we will submit to a journal very soon, as soon as I get some time to read it and finalize it.
Yeah, and I get some feedback from my team now. It's already available on the webpage, so you can find it on the webpage, our webpage as well, the entire report. And otherwise, my follow-up question to you: you mentioned concrete as an upcoming project.
Yes.
Do you see any more things that you want to do in the future in your research with biochar?
Yes, we see it as extremely, there's a huge interest in biochar. Recently, I was in a meeting with AB3C supercluster. It's a mixture of universities and companies in northern Nordic countries. So Norway, Sweden, and Finland. And they have extreme interest in biochar, especially the small and upcoming startup construction companies. They are very interested in using biochar in concrete to make it sustainable, because they have a big problem with the cement being a very high carbon footprint material. So concrete is definitely big, and where we can use high amount of biochar. Like in plastics, the amount of biochar is not too high. But in concrete, the total volume of biochar will be much higher, which means more waste can be valorized or value added, reducing the pollution. So it is a more sustainable route. But again, like I said, I did quite a lot of studies during my PhD, and after that, we did a lot of research on biochar-based plastics. But we don't know much about how biochar affects concrete or cement. So that is a huge potential for research. So these two areas we would like to move forward with, like biochar in plastics, different types of plastic, like common polypropylene, which has already been done quite a lot. Polyethylene also, there's quite a lot of work done on that. Concrete is an upcoming material. A lot of people in the around the world are working on it. So these are the two materials that we would like to work. But from the question, we would like to also look into the effect of doped biochar in paints. And we cannot sadly apply biochar in wood because it has to be mixed. So wood is already formed material. But if we are making paint, intumescent paint, we can be using it in wooden structures. That is something we would like to work with our campus in Skellefteå. They do a lot of wood science studies. We will be collaborating with them. Edita is there, and then there are other people who are working on the fire safety of wooden structures, and we would like to collaborate with them. So yeah, so plastic, concrete, and biochar-based paints in wood. That is our next target. Rhoda might have some other. Rhoda, do you have maybe some artificial intelligence?
Yeah, and and also for the insulation materials, the application of biochar in insulation materials, I think that's also a viable place to consider.
Oh yeah, right. And it's a lot of materials upcoming, like cellulose for environmentally friendly insulation materials, of course. It sounds very interesting. Yeah. So there's a lot of room for new materials, but also new collaborations, and to refine and develop more things out of this. That sounds very interesting. Yes. And I hope you get a lot of good contact in the audience today. So.
Yes, and that's why I'm very thankful to Brandforce for providing this arena where we can share our views and go towards a common goal. Like, I always said in science, everyone is winning. No one is losing. Like, I know there's a lot of competition for like funding and everything, but when it comes to science and engineering, everyone is winning because we are trying to find a solution for the society and as a whole together.
Yeah, that's excellent. Okay, I think we've answered all the questions. Thank you so much for all the good questions, and thank you for your answers. Anything else you want to add?
No, not right now, but maybe when we discuss, things will come up.
Yeah. And as I said, this is to be continued. You are starting up a concrete project, and we will present that after next summer, so in about a year.
Exactly.
And of course, I can mention that to the audience. If you are interested in participating in the reference groups to our projects, you are very welcome to get in touch with us, and we will see to any possibilities of that, of course. So, thank you so much, Rhoda and Isaac.
Thank you.
Thanks, too.
Now I'm just going to wrap things up here and tell you a bit more about what is upcoming at Brandforsk in the near future. And again, I like to mention our funding is still open if you want to chip in, and also thank you to everyone that already has. Of course, just please contact us if you are interested in being a supporting organization here. And you can always see what is going on our web page, and also following us if you follow us at LinkedIn and other social media, and also our YouTube channel. We have a few webinars coming up quite soon. They will be in Swedish. Among many things, we will talk about from one of our researchers in our research school. We'll talk about part-time firefighters, and we are also to present our very newly released book. It's published at Springer. It's about residential fire safety, The book is in English, and you are very welcome to find that at the Springer webpage. And the webinar will be in Swedish. And we are looking into different things to do in English as well about that book. And the book is a result of many years of research in Sweden and also in other countries. So I think it really wraps up this topic very well. And of course, if you have any suggestions yourself about webinars that you would like to see, please contact us, and we will look in what to do about it. And also, if you want to keep informed about what's going on here, you can sign up for our newsletter. And thank you, Oisik and Rhoda, and thank you to my colleagues, Francis Eurenius and Matthias Hamrin, that has been producing this webinar. And again, thank you to all our supporting organizations. So that's it. Thank you for listening, and thank you for all the good questions. I hope that you will have a nice weekend. It's Friday today, and please answer our questionnaire. And also, if you have any other thoughts you want to share with us, just get in touch with us. Thank you. Bye-bye.